Hey, what's up there, Calc 2 crew, and welcome back to another one of our daily problem sets. And today we're going to be taking a look at Taylor and Maclaurin series in section 11.10. A Taylor series is a series centered about x equals a, and in the special case when we have a Taylor series centered at 0, we call that a Maclaurin series. So a Maclaurin series is really a Taylor series centered at x equals 0, when a is 0. And we have the following definition. So for a Taylor series centered at x equals a, we have the function f of x can be written as an infinite degree polynomial, and that's the sum from n equals 0 to infinity of, we have f's nth order derivative evaluated at a, all divided by n factorial, and then times x minus a to the power of n. And if I write this out longhand to see the terms of the polynomial, we have f at a plus f prime at a over 1 factorial times x minus a, plus f double prime at a divided by 2 factorial times x minus a squared, plus now we have f's third order derivative evaluated at a divided by 3 factorial times x minus a cubed, plus so on and so forth. And usually, right around the third order derivative, we stop using this prime notation, and we start using superscripts with parentheses, and then inside the parentheses we have a number indicating the order of the derivative. So we'll be using that notation, because otherwise if you get to, let's say, the 10th order derivative, well, it's going to be kind of tricky. What do you do then? Do you keep doing the prime? Do you use Roman numerals? Haha, lol. And this is the Taylor series expansion at x equals a. Now if I want to talk about a Maclaurin series, that means I'm centering it at 0, so we can write this as an infinite degree polynomial but centered at 0. We have the sum from n equals 0 to infinity of f's nth order derivative at 0 divided by n factorial times x to the n. And I could write this out longhand. We have f at 0 plus f prime at 0 over 1 factorial times x, plus f double prime at 0 divided by 2 factorial times x squared, plus f's third order derivative evaluated at 0 divided by 3 factorial times x cubed, plus so on and so forth. And I actually want to point out that this isn't brand new calculus for us. It's actually a continuation on something that you've done. So in Calc 1, you would have worked with linearization. With linearization, though, you actually only looked at the first 2 terms of a Taylor series. So this would have been from your Calc 1 linearization. And now we're actually just continuing this process, and we're seeing the pattern a bit better. We didn't really worry about dividing by 1 factorial back when we were in Calc 1, because you could say, well, 1 factorial is 1, so I don't really need it. We would just have f at a plus f prime at a times x minus a would be our linearization function. But I can actually better recognize the pattern here and continue it to start talking about, Taylor series, which is great. Now, in the book that we're working out of, and maybe this page has sort of migrated a bit between different editions, we do have a table of common expansions for different Taylor series and Maclaurin series. I don't really think it's worth your time to stare at this too much or try to memorize it. That's not really the idea. That's not really the goal. But it exists, and here's a small sampling of it if you're interested. I mean, we're familiar with this 1 over 1 minus x as well. We talked about that recently. We can see exponential functions, trigonometric functions, inverse, binomial expansions, all sorts of cool stuff. But we're here to focus on building these Taylor and Maclaurin series ourselves. We're going to take a look at a couple of examples because these can be long examples. So here I want to find the Maclaurin series for f of x using the definition of a Maclaurin series. We're going to assume that f has a power series expansion. We're not going to worry about showing that the remainder of the series goes to 0, the Pinel remainder. And I also have this follow-up to find the radius of convergence as well. We're not going to do that together. However, I do encourage you to find the radius of convergence. Remember how we do that? We would use ratio test. But so for what we're doing today, I'm just going to say, well, we're just going to find the Maclaurin series, and that should be good enough. Let's talk strategy. What are we going to do? Well, glad you asked. We're going to find a lot of derivatives. And then after we have the original function and a lot of derivatives for it, we're then going to evaluate the original function and all of the derivatives at 0. Since we have a Maclaurin series, that means a equals 0. So I'm going to plug in 0. And then from there, I'm going to try to build coefficients to the series. I don't want to forget about dividing by factorials. So it takes a good amount of practice and seeing and working through enough examples to really get comfortable with building Maclaurin series on our own. Let's go ahead and jump in and see what we can do. So here I have f of x is 6 times parentheses 1 minus x all to the power of minus 2. Let's get differentiating. If I find f prime of x, we'll say 6 comes along for the ride as my coefficient. The derivative of stuff to the power of minus 2 gives me minus 2 stuff to the power of minus 3. I want my inner function back inside, which is 1 minus x. And then I want to multiply by the inner derivative. Derivative of 1 minus x is negative 1. Now I do want to clean this up a bit as I go along, but it's my personal sort of advice to you to not multiply things out. I think if you clean up too much and if you multiply things out too much, that you really run the risk of missing out on what it is the pattern is supposed to be. So let me just write this as we have f prime of x. Here I have 6, and then negative 2 times negative 1 on the other side here, that's going to be positive. I'm going to write it as positive 2 times 1, and then 1 minus x to the power of minus 3. And I think that's good for the first derivative. Now let's move on and find the second derivative, f double prime of x. So now my 6 times 2 times 1, and I purposefully didn't multiply this out, it's just some coefficient, right? It's 12, right? But let's leave it like this. This is going to come along for the ride, 6 times 2 times 1, and the derivative of stuff to the power of minus 3 is going to give me minus 3 stuff to the power of minus 4. I can write the inner function back inside, but now I have to multiply by the inner derivative, finishing my chain rule. Derivative of 1 minus x gives me negative 1. And I'm going to clean this one up as well. So here I have 6 times, I want you to notice that the negative 3 times the negative 1, flip the sign to positive, so sort of undoing the minus signs there. But I'm going to bring the 3 closer to the front and say, 3 times 2 times 1. There's 3 times 2 times 1. I have another 1, but I don't need to multiply by a whole bunch of 1s. It's not going to really help much. And then 1 minus x to the power of minus 4. I think that looks good for the second derivative. Let's find the third order derivative. Same idea here. This is my coefficient. It's going to come along for the ride. 6 times 3 times 2 times 1. The derivative of stuff to the power of minus 4 is going to give me minus 4 stuff to the power of minus 5. My inner function, I can write it back inside. And then the derivative of my inner function gives me negative 1. I can clean this up as well. Notice a negative times a negative is back to positive. So I have this 6 in front, but then here I have, 4 times 3 times 2 times 1. And then this 1 minus x to the power of negative 5. And I want to find derivatives so that I can start to see a pattern establish. So I would go ahead and I would maybe keep doing this, maybe find up to the 4th or the 5th order derivative, somewhere along those lines. Hopefully that gives us enough usable content. If I find the 4th order derivative, here I'd say, well, this is all my coefficient. I haven't been multiplying it out. Might seem weird to not do that in a math class, but I think it's better for noticing the pattern. And the derivative of stuff to the minus 5 is going to give me minus 5 stuff to the power of minus 6. My inner function, 1 minus x, is back inside, times the derivative of my inner function, which is a negative 1. And I can clean this up. Notice negative 5 times negative 1 brings me back to positive. So I have 6 times, I'll bring the 5 to the front, 5 times 4 times 3 times 2 times 1, and then this 1 minus x to the power of negative 6. And keep differentiating so that you can find that pattern. I'm going to stop here and start evaluating, but if you don't have enough information, go and find more derivatives. Right? And be careful when you find those derivatives, because if the derivatives are incorrect, then it's going to throw off your answer, and we don't want that, definitely not. But once I have enough derivatives, here I have up to the 4th order derivative, I then want to go to my original function as well as the derivatives that I found, and since I have a Maclaurin series, that means a series centered at a equals 0, that means I want to evaluate all of these at 0. So if I go to f of x and I evaluate f at 0, that means plugging 0 in for x. I get 6 times. Here I have 1 minus 0 to the power of minus 2. Or that's 6 times. Here I have 1 to the power of minus 2. 1 to the power of minus 2 is really just 1. So 6 times 1. So this gives me 6 for f at 0. So f at 0 is 6. And I want to do this with my derivatives. So let's go to f prime and plug 0 into that. So f prime at 0. You say, well, if I plug 0 in, I want you to notice I'm going to get 6 times 2 times 1 times 1 minus 0 to the power of negative 3. And this is really 1 to the power of minus 3, which is just 1. So this leaves me with 6 times 2 times 1 for f prime at 0. If I go to my second order derivative and plug 0 in for x, so f double prime at 0, I get 6 times 3 times 2 times 1 times 1 minus 0 to the power of negative 4, and this is 1 to the power of minus 4, which is just 1. You think of it as 1 over 1 to the 4th, something like that. So this is just 1, so I'm just left with 6 times 3 times 2 times 1 for f double prime at 0. And I got a couple more, so let's find my third order derivative evaluated at 0. So it's going to give me 6 times 4 times 3 times 2 times 1 times 1 minus 0 to the power of minus 5, which is 1 to the negative 5, which is just 1. So this gives me 6 times 4 times 3 times 2 times 1 for my third order derivative evaluated at 0. And I went up to the fourth order derivative, so let's evaluate that at 0 as well. You probably know what's going to happen. Let me know in the comments below. 6 times 5 times 4 times 3 times 2 times 1. Happy birthday! Times 1 minus 0 to the power of negative 6. That's 1 to the negative 6, which is just 1. So here I get 6 times 5 times 4 times 3 times 2 times 1 for my fourth order derivative evaluated at 0. Now there's definitely a pattern that's sort of emerging here, and I want to be careful with how I view this, especially where I stopped, right? Because that I think could be a bit misleading almost, depending on how I'm trying to write this. So I think sometimes it's easiest to look at the pattern as we go far enough out. Right? The pattern maybe isn't so obvious at first, but once we see more and more and more of these pieces, we start to recognize what the pattern actually is. However, where I ended is kind of a bit tricky, because I don't want to think about this 6 that I have in front too much, because in fact all of them have that 6. That was a coefficient on the function that I had. So everyone's really got the obligatory 6. But let's see if we can see the pattern otherwise. So I think it helps maybe to even look at these last two together. I notice here I have a 6 and I have 4 times 3 times 2 times 1. I could think of that sort of as a 4 factorial. And here I have a 6, but now I have also a 5 times 4 times 3 times 2 times 1. So like a 5 factorial. And we can start to get a good idea as to what's happening here. So let me jot down some ideas. So we have, f at 0 we want to talk about, f prime at 0, f double prime at 0, f's third order derivative at 0, and f's fourth order derivative at 0. And if I'm saying what I'm sort of noticing when I'm looking at the fourth and the third order derivative evaluated at 0, we said, well, the third order derivative at 0, it's like a 6 times a 4 factorial. I think that's a really good way to express it, 6 times 4 factorial. Where my fourth order derivative at 0, I have a 6 and then a 5 factorial. And I could write that as 6 factorial, but it's actually not going to be the most helpful to write it that way, because it's going to break the pattern a bit. So write it as 6 times 5 factorial. But what about my second order derivative at 0? Well, this is a 6 times a 3 factorial. So now we can start to maybe see the pattern a bit. When I go to the first order derivative at 0, well, this is a 6 times a 2 factorial. Yes. Yes, of course. And f at 0, that was just 6. But if I want to try to fit it to this pattern, I can do that at no extra cost. I could say this is 6 times 1 factorial, because 1 factorial is just 1, and 6 times 1 is still just 6. So here I have a really good idea as to how I can, categorize what it is I'm working with. Now from here, a good question is, okay, well now how can we build our Maclaurin series? I'm glad that you asked. What I like to do is I like to actually write out the Maclaurin series longhand first, as sort of its polynomial expansion. So we would want to start with f at 0, and then I want to add to this, now I want f prime at 0 divided by 1 factorial times x. Then I want f double prime at 0 divided by 2 factorial times x squared. Then I want my third order derivative evaluated at 0 over 3 factorial times x cubed. And then I want my fourth order derivative evaluated at 0 divided by 4 factorial times x to the fourth, and then so on and so forth. If I had more of these terms, I would use them. And this is just the familiar definition that we had on this first page, right here. I'm just writing this out. And now I want to include what I have for the problem. So we said f at 0 was 6 times 1 factorial. Plus f prime at 0 was 6 times 2 factorial, and then divided by 1 factorial. I don't want to forget to divide by these factorials. And I don't want to forget my x terms as well, my power terms. F double prime at 0, remember that was 6 times 3 factorial, and then divided by 2 factorial times x squared. I could sort of scooch up here, there it was, 6 times 3 factorial. And then my third order derivative at 0, well, that was 6 times 4 factorial. But then I have to remember, I'm responsible for remembering, hey, divide by 3 factorial, hey, multiply by x cubed. And my fourth order derivative at 0 was 6 times 5 factorial. So say, okay, plus, we have 6 times 5 factorial, and I'm responsible for remembering divide by 4 factorial, multiply by x to the fourth. And this process would continue on and on and on. It's only stopping because, I stopped at this point hoping I had enough info. Now, everybody has a 6. I don't want to mess around with that because that's something that's common of all of these coefficients. But for the rest of these coefficients, I can actually simplify. So notice here, if I start at the end, so I'll do plus dot dot dot, but then I'll move back from there. 5 factorial divided by 4 factorial is just going to give me 5. So I have 6 times 5 times x to the fourth. And let's move backwards. So here's my x cubed term, but I have a 4 factorial divided by 3 factorial is going to leave me with 4. So I have 6 times 4. And here's my x squared term. 3 factorial divided by 2 factorial leaves me with 6 times 3. I have that 6 there, and then I'm left with the 3. Here's my x term. 2 factorial divided by 1 factorial is going to give me 2, so I have 6 times 2 times x. And then here, if I just want to try to notice what's happening, the pattern's really starting to become clear now in my Maclaurin series. Well, this is a 6 times 1. And you could say times x to the 0, but it's just a constant term. And now that I have this, I can really start to see what's going on. Right? And now I can actually try to think about how I could write this in a closed form. And that's always going to be my goal. And it's about this pattern recognition. We get better at it with practice. But here I could say this is the sum from n equals 0 to infinity of, and if it helps, I could sort of go to this very first one here, and I could write in the x to the power of 0. Though it's really kind of, hidden. X to the 0 is just 1, so it's not really visible. But if I write it in, I can sort of stare at it a bit and say, well, okay, so all of my power terms should be x to the power of n, starting at 0 and increasing. So x to the power of n We have x to the 0, x to the first, x to the second, x to the third, x to the fourth, so x to the n starting at 0. And then everybody has a 6. So 6 is going to be there, the obligatory 6. But then how can I write my coefficient? Here I have a 1x to, well, the rest of it I should say. I have a 1x to the 0. I have a 2x to the first. I have a 3x to the second. I have a 4x cubed. I have a 5x to the fourth. If my exponent is n, this number, in front of it, after the 6, of course, should be 1 higher. It should be n plus 1. So that's n plus 1. And this is going to be my power series, my Maclaurin series, centered at 0 that I just constructed. And this is maybe a bit of a crazy idea, but the idea is that I can take this function, and this was 6 times 1 minus x all to the power of minus 2. So 6 times 1 minus x to the power of minus 2. We're saying this function can be written as this infinite degree polynomial and converges to it. So this is what we get. We get this power series. Now we're going to forego finding the radius of convergence. I have some space for you to work on that on your own, but that's good practice for ratio test. Remember how we did that back in 11.8? We would use ratio test. Here I got the space. So use ratio test. You know how to do it. You know what you're doing. Let's take a look at one more. I want to find the Maclaurin series for f of x. Again, we're going to assume that there is a power series expansion. We're not going to worry about the remainder of the series. We're going to not worry about showing that it goes to 0. I do want you to find the radius of convergence for practice with ratio test, but we're not going to do that together since we did that just a bit ago. But let's go ahead and find our Maclaurin series. And here we have the function ln of 1 plus 5x. Remember, Maclaurin series means centered at a equals 0. If I find f prime of x, the derivative of natural log of 1 plus 5x, I need chain rule. Derivative of natural log of stuff is 1 over stuff. So that's 1 over 1 plus 5x. And then times the inner derivative is 5. And since I have to differentiate this again and again and again, I am going to clean this up. I'm going to write this as 5 times, so here's my 5, times 1 plus 5x to the power of minus 1. And then I can go ahead and find my second order derivative. So I'll say, okay, well now 5 comes along as this coefficient. Derivative of stuff to the minus 1 is minus 1 times 1 plus 5x all to the power of minus 2 times the inner derivative, which is 5. And I don't want to multiply this out, but I do want to kind of collect as best as I can. So here I would say I have 5 times 5. Maybe not a bad idea to write that as a 5 squared. And then I have this negative 1 times 1 plus 5x to the power of minus 2. And I can move on to my third order derivative. I'll say, okay, so then 5 squared times negative 1 comes along for the ride. The derivative of stuff to the minus 2 gives me minus 2 stuff to the power of minus 3. 1 plus 5x, I can write that back inside. And then the inner derivative gives me 5. And if I want to clean this up, we'll say, well, 5 squared times 5 gives me 5 cubed. And then I have negative 1 times negative 2 becomes positive. So I'll write this as positive 2 times 1 times 1 plus 5x to the power of minus 3. And I'll differentiate. I'll find the fourth order derivative. So now my 5 cubed times 2 times 1 is coming along. The derivative of stuff to the minus 3 gives me minus 3 stuff to the power of minus 4. I can write my 1 plus 5x back inside, and then the inner derivative gives me another 5. And if I'm noticing what's happening, I'm back to being negative again. And I have 5 times 5 cubed is 5 to the 4th. And then I have this, negative 3 times 2 times 1 times 1 plus 5x to the power of minus 4. And maybe we'll find one more derivative here. We'll go up to the 5th derivative this time. What a treat. So here I have this 5 to the 4th times, I have negative 3 times 2 times 1, comes along as my coefficient. Derivative of stuff to the minus 4 is minus 4 stuff to the power of minus 5. I can write my inner function 1 plus 5x back inside. And then the derivative of my inner function gives me 5. And now cleaning this up, well, now I have a 5 to the 5th. Right? I have 5 to the 4th times 5 is 5 to the 5th. And notice I'm back to being positive. Negative times negative is positive. And I have this 4 times 3 times 2 times 1 plus 5x to the power of minus 5. And so on and so forth. If I want to find more derivatives, I certainly can and get more information that way. Now I want to start evaluating. We said Maclaurin series, which means centered at a equals 0. So I want to plug 0 in and evaluate, starting with the original function. So here that was given to me, so I could have done that already. If I plug 0 in, I get f at 0 is natural log of 1 plus 5 times 0. 5 times 0 is 0, so this just gives me ln of 1. And important to remember that natural log of 1 is actually 0. So f at 0 is actually equal to 0. And then I want to evaluate my derivatives now. So I want f prime at 0. And this example is not too dissimilar from the one we just saw, in fact. If I plug 0 in for x, so I get 5 times 1 plus 5 times 0 to the power of minus 1. This becomes 1 plus 0 to the power of minus 1, or that's 1 to the power of minus 1, which is just 1. So this gives me 5 for f prime at 0. And if I keep that in mind a bit as I go through the rest of these, for f double prime at 0, we'd say, well, here when I plug the 0 in, I get 1 to the power of minus 2, which is just 1. So I'm left with 5 squared times negative 1. And when I plug 0 into my third order derivative, again, keep in mind, 5 times 0 is 0, 1 plus 0 is 1, 1 to the power of minus 3 is just 1, so I'm really just left with this coefficient, 5 cubed times 2 times 1. And we have a couple more. If I take a look at my fourth order derivative evaluated at 0, I plug 0 in, I get 1 to the power of minus 4, and this is just going to give me 1. So I'm left with 5 to the 4th times negative 3 times 2 times 1. And if I take a look at my fifth order derivative, and this is as far as we went, my fifth order derivative evaluated at 0, I'm going to get 1 plus 5 times 0 to the power of minus 5. And that's 1 to the power of minus 5, which is just 1. So I'm left here with this coefficient, 5 to the 5th, times 4, times 3, times 2, times 1. But now I can go through and try to see if there's any maybe slightly better way I can write this for where I'm going next with it. So let me get some space down here. We want f at 0, f prime at 0, f double prime at 0, f's third order derivative at 0, we got a fourth order derivative at 0, and then we had the fifth order derivative at 0 to discuss. And I like to start by looking at the end to start to see the pattern. I noticed, though, that I had this kind of minus sign creeping in every other term, it looked like. So if I'm sort of focusing on what's happening here, for this fourth order derivative, it is negative, but otherwise I see 5 to the 4th, and then I see a 3 factorial. So for the fourth order derivative, I might even start there. I'll say, well, that's negative, and that was 5 to the 4th times, what was that, a 3 factorial we said? Yeah, 5 to the 4th, it's negative 3 factorial. So I got my negative 5 to the 4th, 3 factorial. Well, then what about the fifth order derivative where we ended up? And that was positive, but it was 5 to the 5th and then 4 factorial. So this one was positive, 5 to the 5th, 4 factorial. Since I have that sort of alternating sign, sort of going, positive, negative, positive, that third order derivative at 0, I bet that one was positive, wasn't it? It looks like I have 5 cubed and then a 2 factorial, and it is positive. 5 cubed times 2 factorial. And then I bet f double prime was negative. Yeah, so it was a negative 5 squared times 1. And if I'm trying to be good, if I'm trying to follow and establish a pattern, I would say negative 5 squared, and then we could say 1 factorial. And we could say that for free. 1 factorial is just 1. The multiplicative identity, we can say that, no problem. And we can start to really get an idea as to what we're expecting. So now I'm expecting, okay, so it's going to be positive for f prime 0. It's going to be 5 to the first, which is 5. And then 0 factorial, we define 0 factorial to be 1. So I'm guessing this is just positive 5 to the first, or just 5. Let's see, f prime at 0, were you positive 5? You were positive 5. And f at 0 was 0. So I can throw that in as well. Now, we don't quite have our coefficients yet, but we have all the hard work kind of out of the way. We just have a little bit left to go. Now remember, what I like to do next is I like to write out a very generic idea of how a Maclaurin series should look. It's good experience with the formula as well. So this would be f at 0 plus f prime at 0 over 1 factorial times x plus f double prime at 0 over 2 factorial times x squared plus f's third order derivative at 0 over 3 factorial times x cubed, f's fourth order derivative at 0 over 4 factorial times x to the fourth, f's fifth order derivative at 0 over 5 factorial times x to the fifth, and so on and so forth. But now I want to start dropping in the information that I have from these. So let's see what we said. We said f at 0 was 0, plus f prime at 0 was 5 over 1 factorial x, plus f double prime at 0 was a negative 5 squared times 1 factorial. So negative 5 squared times 1 factorial. But I have to remember, divide by 2 factorial, multiply by x squared. I'm responsible for dividing by the factorials, multiplying by the power terms. The third order derivative at 0 was 5 cubed times 2 factorial. So that's on the top there, 5 cubed times 2 factorial. But I have to remember, divide by 3 factorial, multiply by x cubed. My fourth order derivative at 0 was negative 5 to the fourth times 3 factorial. So that's on top, negative 5 to the fourth times 3 factorial. But I have to remember to divide by 4 factorial and multiply by x to the fourth. And then lastly, we went up to the fifth order derivative at 0. That's 5 to the fifth times 4 factorial. That goes in the numerator. 5 to the fifth times 4 factorial. But I have to remember to divide by 5 factorial and multiply by x to the fifth. And this would continue on and on and on. Right? I'm the reason why it stopped. Well, let's see if we can simplify this at all. I have this nice pattern with the 5s. I don't really want to, mess around with that too much. But I do notice as I get further out, I have factorials that I'm dividing. I have this quotient, 4 factorial over 5 factorial, for example, and I can reduce that. If I think of 5 factorial as 5 times a 4 factorial, I can cancel a 4 times 3 times 2 times 1 on top and bottom, and I'm left with a 5 in the denominator here. So I'd go and I would say, well, this is 5 to the fifth divided by 5 times x to the fifth. Now I'm trying to keep my cool because I really want to reduce. But I think if I reduce, I'm going to disrupt the pattern. So I'm not going to do that yet. I don't think it's maybe a good idea to. I'm trying to avoid temptation. What about x to the fourth? I have this 3 factorial over 4 factorial. It's going to cancel, leaving me with just a 4 in the bottom. But then on top, I still have this negative 5 to the fourth. For the x cubed terms coefficient, I have a 2 factorial divided by 3 factorial. It's going to leave me with a 3 on bottom, and then a 5 cubed on top. For my x squared term, I have 1 factorial divided by 2 factorial is going to leave me with 2 in the bottom. And then on top I have a negative 5 squared. And then for my x term here, if I'm sort of noticing the countdown happening in the denominator, that's going to be a 1 in the bottom. 1 factorial is 1. And then I really have a 5 to the first on top. And I have this 0 that I'm starting with, but since it's a 0, adding it doesn't really help. So maybe you're going to not even write that. But maybe now we can start to see the pattern emerge from this. And let's see if we can't try to write this in some closed form for a power series. So let's say the sum from n equals 0 to infinity. And we'll discuss another way we could write this. Let me start with the power terms. Since that constant term is actually 0, it kind of died off. It's not there. So my goal then is to really think about skipping it. So I should start it at x to the first. And if my starting index is a 0, I would want that to be x to the power of, it should be n plus 1. So that I'm starting at x to the first and then going from there. We'll talk about another way we could write this in just a bit. Now from there, let's talk about what else we have. In the denominator, whatever the exponent is, I'm mimicking that in the denominator right away. X to the fifth, I'm dividing by 5. X to the fourth, I'm dividing by 4. X cubed, I'm dividing by 3. X squared, I'm dividing by 2. X to the first, I'm dividing by 1. So if it's x to the n plus 1, then I'm dividing by n plus 1 as well. I also have these 5 to some power, right? And the exponent on base 5 is the same as the exponent on x, and the same as the number I'm dividing by, right? 5 to the fifth, x to the fifth over 5. 5 to the fourth, x to the fourth over 4. 5 cubed, x cubed over 3. 5 squared, x squared over 2. 5 to the first, x to the first over 1. So that's 5 to the power of n plus 1. The only thing that I haven't dealt with yet is the alternating sign. So I know how that's going to have to look. It's going to have to be -1 to some power. But I want to be sort of careful here. The first term is positive, the second term is negative. So if my starting index is n equals 0, well, what I can do is I can actually do -1 to the power of n. And we'll say, okay, so then the first term, it's -1 to the 0, which is +1, which is positive. The next term, when n is 1, is -1 to the first, which is -1. So that's going to be negative. And then the next one, when n is 2, I get -1 squared is positive. So this is going to give me the correct alternating sign. Now, this might not be your favorite way to write this, though it does certainly work. This is going to give us the power series that we're looking for. But there is sort of a nice way that I could write this, so I don't have all of this mention of n plus 1. And in fact, what I could do is I could say, let me start the series at n equals 1 instead. So now, since I'm not starting at n equals 0, I can get away with x to the power of n, because that's going to start at x to the first, and then x squared, and then x cubed, and then x to the fourth. And this is maybe going to look a little bit nicer aesthetically too, because if it's x to the n, I'm also dividing by n. I'm dividing by n. And my powers on 5 should be 5 to the n if I have x to the n and I'm dividing by n. Oh, here's where I'm looking. X to the n, 5 to the n, divided by n for all of these. They should follow suit. So I could say 5 to the n. But then I just have to be careful with my alternating sign again. It should be -1 to some power. And the power should be, something on n. I want this first term to be positive. So if I just write -1 to the n again, that's going to be a problem. That's going to make my first term negative. So I could either do n plus 1 or n minus 1. I think n minus 1 would be nice here. And this is also the same power series representation. Now there are some other things you could do with this from here. I think this looks nice depending on what you want to do with it, because I can see that it's alternating. I can see the power term, and I can see, aside from the alternating sign, the rest of the coefficient where I have these powers on base 5 and I'm dividing by, this value that's growing, same as the exponents. If you do want to try to write this a little bit in a more concise way, and maybe that's something that you're interested in, you could say sum from n equals 1 to infinity. I'm going to say negative 1 to the n minus 1. And then here I could say, since it's x to the n and 5 to the n, I could write that as a 5x collected to the power of n over n. And this looks nice for a different reason. Certainly nothing bad about writing it this way. But I think maybe my preference might even be this, depending on what I'm doing with the power series. But again, a very interesting idea that what I have here, this infinite degree polynomial, is really just some polynomial representation of the original function, which was ln of 1 plus 5x. So what we're saying is ln of 1 plus 5x will converge to this infinite degree polynomial. This is some representation that I have of it that I could be working with. And it's a crazy idea to consider, but we really just have this extreme linearization that is no longer linear and continues on and on and on to build this infinite degree polynomial. And I think it's really quite incredible, right? We'd say there must be some discrepancy, right, between the polynomial and then the function that we're making that into a polynomial. But it keeps correcting, right? As soon as we think there's going to be some distinction between the two, well, there's another polynomial term of high degree that fixes it. And then if we go further out, well, now they have to sort of move apart from each other, but then we keep adding on to that polynomial. We keep improving on it. We keep building it better and better. So we're really able to try to match this function, this curve, line by line, play by play. We're constantly improving this polynomial because it is infinite degree. And that's key here, is we never stop building this polynomial. So we're able to claim that it really does match this function perfectly, right? Really cool stuff. Hey, thanks for talking to me about Maclaurin Series. Thanks for spending your time with me. If you've been watching these videos, I just want to say thank you. Thank you for your time. I appreciate you. And hey, no matter what, I want you to always remember, hey, always keep learning, keep dreaming, follow your heart. I'm not going anywhere. I will see you next time. We're going to do some more math together. But thank you for joining me on this journey through Calc 2. And hey, take care. I'll see you soon.